Hello everyone, myself Dr. Harishankar Singh. In this video, I will be giving the details of magnetic scalar and vector potential. So let's start. Some electrostatic problems become simpler by relating the electric potential V to the electric field intensity E. In the electrostatics, we have defined as E is equal to minus del V. Similarly, we can define the potential associated with magnetostatic field B. The idea is that B should be defined in such a way that divergence of V should be equal to 0. In fact, the magnetic potential could be scalar denoted by Vm. Here M subscript denoted as magnetostatics or vector denoted as A. Let us use following two identities which I have discussed earlier during the discussion of vector in the previous videos. So we know that the curl of gradient of any scalar function V is 0. That is del cross del V is equal to 0, where V is the scalar function. And also we know that the divergence of curl of any vector A is 0. That means del dot del cross A is equal to 0, where A is the vector quantity. These two identities must hold for any scalar field V and vector field A. Now we define the magnetic scalar potential Vm and which relates with H. So we have H is equal to minus del Vm, and according to Ampere's law we know that J is equal to del cross H, and we define H is equal to minus del Vm. After putting the value of H, we will get J is equal to del cross minus of del Vm. And we have defined the vector identity, that is the del cross del V is equal to 0, and when we will apply this identity, we will have del cross minus del Vm as 0. Thus, the magnetic scalar potential Vm is only defined in the region where J is equal to 0. This is useful term for defining the parameter of a permanent magnet. Now, Vm satisfies Laplace equation just as V does for the electrostatic field. Hence, in the Laplace equation, we know as del square Vm is equal to 0, and this is only valid when J is equal to 0. To satisfy equation, we have below two equations, that is del dot B is equal to 0, and another equation we have del dot del cross A is equal to 0. So on equating these two equations, we will have V is equal to del cross A. That means magnetic field intensity related with the magnetic vector potential A in the form of V is equal to del cross A. As we have defined in the electrostatics, vector potential V as integral of dq divided by 4 pi epsilon naught r. Similarly, in the magnetostatics, we can define the magnetic vector potential A for the line current, surface current and the volume current. So for the line current, magnetic vector potential A can be written as line integral mu naught I dl divided by 4 pi r. For the surface current, magnetic vector potential A can be written as surface integral mu naught k ds divided by 4 pi r. And for the volume current, magnetic vector potential A can be written as volume integral mu naught j dv divided by 4 pi r, where I is the line current, k is the surface current and j is the volume current. So we can express the flux alternatively as we know that flux is equal to surface integral B dot ds, and earlier we have defined V is equal to del cross A. That means in terms of magnetic vector potential A. So we can write psi is equal to surface integral del cross A dot ds. And from the Stokes theorem, we can convert the surface integral into the line integral. So we can write psi is equal to line integral A dot dl over contour C. Thus, the magnetic flux through a given area can be found by using the magnetic vector potential A. Also, the magnetic field can be determined using either Vm or magnetic vector potential A. This choice is dependent on the type of problem, except that Vm can be used only in a source-free region. The use of magnetic vector potential provides a powerful approach to solve electromagnetic problems, particularly those relating to antenna. For antennas, it is more convenient to find the magnetic vector potential A rather than finding the magnetic flux B. Thank you for watching this video.